Okay, this video is on ionic and covalent bonds, lattice energy, and then Lewis structures. Okay, drawing Lewis structures. Okay, so real quick, the first part of this lecture is on ionic bonding. And so obviously an ionic bond is the attraction of a positive and negative ion, a metal or a nonmetal. Okay, so I defined it as the force existing between ions of opposite charge. It involves the transfer of electrons. So, our most famous example is the sodium ion and the chlorine ion forming NaCl. Okay, so ionic compounds are stable, and that results because of the attraction of the opposite charges, drawing the ions together. Okay, this process releases energy when the bond is formed and results in a solid lattice of particles. Okay, if you think of the word lattice, most people think of like the, here, let me turn the camera just a little bit so you can see a little better. Okay, most people think of like the, the fencing, like underneath decking sometimes that kind of looks like this, okay? That's, the term used to describe that is a lattice. And basically what a lattice is a repeating pattern. Okay, so when we have ionic compounds, they actually don't exist as molecules per se. They exist as this repeating pattern of the ions over and over again. Okay, so that's what a lattice is. Okay, so we're going to talk now about something called lattice energy, which is the big part of this ionic part of this video. Okay, so what is lattice energy? Lattice energy is defined as the energy required to completely separate a mole of an ionic substance into its ions. Okay, technically speaking, it's the gas state of its ions, but for our purposes, we're really just going to talk about the energy required to separate an ionic substance back into its ions. So basically, it's the opposite of the process that forms the compound. This is the breaking down per se of the compound. Okay, so if you think about it, when a bond is formed, energy is released. So when a bond is broken, it requires energy. Okay, so this process requires energy to break apart our previously formed ionic compound. Okay, so in our previous chapter, we learned about Coulomb's law. Oh, I missed a U in there. Which says that the force of attraction is dependent upon the size of the charges and the distance between them. Okay, if you remember talking about that. So lattice energy basically depends on two things. And those two things are the ion charges and the distance between them. Okay. So the energy required to break apart an ionic substance depends upon the size of the charges that make up that substance and the distance between the charges. Okay, if you remember talking previously about Coulomb's law, higher charged things, when Q1 and Q2 are larger, the force of attraction is higher. When the distance between them is smaller, the force of attraction is also higher. So that's kind of how we're going to relate this to lattice energy. So I'm going to write that lattice energy depends primarily on ion charges, and then only if the charges are the same do we look at the distance between the charges, okay? And that's because, you know, over a wide range, well, I guess I should say ion, the distance between charges and particles doesn't vary that much over the grand scheme of, you know, space, so to speak. So lattice energy basically depends on the charges of the ions. Okay. So just like we learned before, and we'll do this little summary, and then that's pretty much it for lattice energy. So lattice energy, we'll do this. Increases as ion charges increase. Okay, that makes sense. Lattice energy increases as the distance between the charges decreases. And you could take that and switch it around and do the reverse. You know, lattice energy decreases as the ion charges decrease. Okay, or lattice energy decreases as the distance between the particles increases. So you could think about it both ways, but this is kind of our takeaway point here for lattice energy. So if you look, there are 2 questions at the bottom of your paper. So to test your understanding, pause this video, answer those 2 questions, and then unpause it, and I will give you the answers to number 1 and number 2. All right, so number 1 asks you to arrange the following compounds in order of increasing lattice energy. So that means small to large. And we have NaF, we have CSI, and we have CaO. So first thing you want to look at is your charges. This is obviously a +1, -1. This is a +1, -1, and this is a +2, -2. Okay, so it's going to be very obvious that these 2 are the lower lower lattice energies, and this one's the higher one. So we can definitely put CaO as my highest, because remember, it depends primarily on ionic charge. But the issue now is the NaF and the CSI have the same charge. Okay, so only when the charges are the same are we going to look at distance between the 2 ions in this case. So if we think about how Na compares with CS and how F compares with I, that's how we're going to think it through. So Na is much smaller than CS. Think about energy levels in your last chapter. Okay, so Na is much smaller than CS, and F is much smaller than I for the same reason. So because Na and F are the smaller ones, they're going to be, the distance between them is going to be smaller, which means it's going to take a little bit more energy to break it. So NaF is going to be your second one, and your lowest lattice energy is going to be the lattice energy for CSI, because it has the smallest charges and the biggest distance between the 2. So that's number 1. And then number 2, which substance would you expect to have the greatest lattice energy of these 3 listed? Silver chloride is the first one, copper 2 oxide is the second one, and CrN is the third one. So again, if we can get away with just looking at charges, we would look at that first. This is +1, -1, +2, -2, +3, -3. So largest lattice energy would be this guy because it has the largest charge. Okay, so that's pretty much the discussion on lattice energy, and I'm going to go ahead and stop this video and we'll start a new one for covalent bonding.